questions about the midterm?
Should we just be looking at our homework assignments and produce quiz, or should we be looking more in depth on certain topics?
Basically homework questions and quizzes and the study guide that I posted yesterday. Yeah.
I'm not forming the words right in my head. How far up does this extend to? Like how?
It does not cover this week.
Okay.
So this week we started induction, and it's not going to have any induction on it. But it'll have, yeah. But it'll have those first three topics that we did.
Will it have any of the homework for stuff like the encryption stuff? Will that be on there or no?
Could be, yeah.
Okay.
So if this comes up, I don't know if it'll come up or if I've got to trick it. I just downloaded it. So it's basically set theory, propositional logic, and then number theory. Yeah.
So as with the previous quiz, are we only allowed to use one sheet of 8.5 by 11 notes?
Let me make sure what I posted.
You posted open notes.
Open notes. There you go.
Right, but
So you can have as many pages as you want.
even the ones that we took during class?
Yeah.
Okay.
Right.
I'm using this for notes?
Yeah, that's fine.
I think you already said yes, but we can print out text-based ones, right?
Don't print the textbook.
No.
But yeah, your own notes, you can print them out, sure.
I had a quick question on the cryptology.
Okay.
Other than the shift encryption, which other encryptions did we talk about?
We talked about a transposition cipher, where you basically rearrange letters within blocks. So we typically have So we might have a transposition which says block size equals 3. And we might say transpose character 1 to position 2, transpose character 2 to position 1, and maybe transpose character 3 to position 3. We don't change that one. And if we wanted to encrypt this using this encryption cipher, break it into blocks of 3 letters, 3 symbols, and apply the transposition. So character 1 becomes the second character, character 2 becomes the first, and character 3 doesn't change. And there's our encrypted string. And to decrypt, we just reverse these. Right, you just define the reverse shuffling. So we talked about transposition ciphers, and we talked about public key ciphers. And I told you I'm not going to hold you responsible for the details of something like RSA, but you should know the basic idea of a public key system, which is that with most of these encryptions, if you know how to encrypt, you also know how to decrypt, so you have to keep the encryption key secret. With a public key, the encryption key is known to everyone, but only you know the decryption key, and you can't get the decryption from the encryption. That's the unique part of it. And I think I briefly talked about one-way encryption, where you take something and you can turn it into gobbledygook and there's no way to reverse it, practically speaking. And we use that like for password security. I think that was about it.
Okay. So probably transition cipher would be the only one, or like and shift would be the only ones who would actually be computing the output, and the other ones would just.
You might compute for a shift or for a transposition.
Yeah,
But no, I'm not going to ask you to do an RSA or to know the details of how that works.
Okay.
And I'm not going to ask you about details or to do it one way. page.
Are we ignoring spaces?
Yeah. You've got to do something preliminary to your file. So the RSA encryption we talked about only worked on 26 characters. So for that one, we'd get rid of all the spaces and punctuation. We'd make everything uppercase,
You mean
and then we'd encrypt.
the shift we talked about?
Yeah, the shift
RSA
only
was
works from
only-
26 too. Well, when we did RSA, we assigned a 2-digit number from 00 to 25 for each
Right.
character. But yeah, shift is a better example. We just assume uppercase letters. And you either ignore punctuation, or you come up with a more sophisticated algorithm, or you just leave it unchanged, which is a bad policy. Yeah.
When we were talking about cryptology, kept talking about trivial and non-trivial. What is like a definition of what we would say trivial in the case of cryptology?
I don't think that's well defined.
Okay.
When I said trivial in the homework, the problem was I asked for a key that can both encrypt and decrypt. Last time I did that, almost everybody said a key of 0.
Okay. I got you.
And that's really trivial because you're not encrypting, right? Your original string doesn't change. So that's all I meant by that.
Okay.
The bigger question of what's a good cipher or what's a strong cipher, that's way beyond my pay grade. And it changes over time. I suspect the Caesar cipher used to be good.
So fast for non-trivial was just pick an answer that you had to show a little bit of work.
Yeah, yeah. Something that actually changes your input string to something else. Are we looking for aliens already? Yeah. Other questions? You'll have 50 minutes for the exam. I'll probably be able to give you like an extra minute or two, but there's a class right after this one, so keep it close to 50. And it should mostly look like stuff you've done.
So I would imagine the exam would look a lot like quiz 1, just with maybe less modulus, questioning some more on some other topics.
That's probably a reasonable hypothesis. I don't remember what I put on quiz 1. I don't remember what I put on the midterm. But
So it's kind of a surprise for you too.
it's a surprise for me too. I'm like, whoa, did I really ask them that?
Cool.
Yeah.
Let's see what happens.
Yeah.
Oops, I didn't cover that, so.
But I did write it 2 days ago, so I know that we went over all the stuff that's on there. All right, so we were talking about horses and their color, and we had a proposition, P of n, which said all horses in a group of n, and any collection of n horses all have the same color. So if you take n horses and you put them in a field, they're all going to be the same color as each other. And we were trying to show this with induction, and our base case was trivial if we have one horse in a field, it's the same color as every horse in that field because there's just one. So this is true. If we assume P of n, then we have the following if we have our horses that are all the same color, so all the same color. Now if we consider any n plus 1 horses, we can apply P of n to this group, and so these are all the same color. But we can also apply P of n to this group, and these are all the same color. And if all of these horses are the same color as each other, and all of these are the same as this horse, all n plus 1 must be the same color. And so we've proven P of n plus 1. And so all our horses have the same color for any n. So what's the problem? Did you refine your objection?
first of all, you're assuming P of n, and yes, you've proven P of 1, but that's not P of n.
But it never is. That's the point of induction.
I still am objecting to including, using the same statement to prove two separate
The
sides.
green and the red.
Yes.
But suppose n equals 5. Right, so here's 6 horses. Do you agree that all 5 of these must be the same color as each other?
No.
But if you've proven P of 5, P of 5 says any collection of 5 horses all have the same color.
There could be thousands upon thousands upon thousands of collections of 5 horses, so.
And for any collection, all the horses in that collection have the same color. Now, this could be a gray collection, this could be a blue collection. But within any collection, all 5 have to be the same color. Do you agree with that?
No.
Well, what does P of 5 state?
Based on the rules of induction, yes, it's true. But
I think it is true, as long as you are adding the term that the next, which is n plus 1 horse,
Mhm.
should be, when we are adding that to the set, it should be, what was the color? Brown?
Sure.
Yeah, same color.
I think he's on the right
So-
track there. Like, if
Yeah.
we're sitting on the integers, 1, 2, 3, and 4, and we prove that
Yes.
those are all the same color, numbers that are the integers, and then
Mhm.
we add another integer, it's from the same set. So
Right.
it's the same color because it's the same sort of a group of things. Or maybe if we take n plus 1, we've proven that 1 is the same color, so we're adding.
But I can prove that 2 plus 2 plus any number of these is even using mathematical induction.
What I was trying to say was that n plus 1, if it is based on n, it is true. But here it's not based on n. It is true just for that single case.
But P of n by itself says any collection of n horses. P of 5 says any collection of 5 horses, all those 5 horses will have the same color as each
So
other.
that's wrong. The basis that is wrong.
But we're assuming this, and we're trying to show P of 6, or we're assuming P of n and trying to show P of n plus 1.
I think this is too complicated a case for mathematical induction. Because you're not taking into
Because there's
account,
horses.
you're not taking into account the color of the horse when you're adding it.
Right.
So,
Yeah, it's
Yeah.
two different cases,
Yeah,
horses
yeah.
and colors.
right, because the colors of horses are not countably infinite. They're not ordered like adding a set of integers of horses.
Well, I could do this for the age of horses and show all the horses have the same age. You're very close to the problem with this proof.
Is the problem where you're applying P of n to n plus 1 by just shifting a 1? That doesn't seem reasonable. Because
It's unusual, but this is still a set of 5 horses.
yeah, but it's not the P of n you're assuming is true. It's a different P of n.
No, I'm not assuming, P of 5 does not say these 5 horses have the same color. P of 5 says any 5 horses have the same color. It's a really wide sweeping proposition. And we proved it for 1, and so we assume it for n, and we try to show it for n plus 1. So we're allowed to assume any 5 horses have the same color. And so these 5 are all green. If these 5 are all blue, we've got a problem because horse 3 is both green and blue.
But if you say we have a set of 6 horses,
Okay?
then we don't have a set of 5, we have 5 plus 1.
But it's got a set of 5 inside.
I suddenly see the distinction you're making.
Yeah.
You're saying that this collection is the same, and this collection is the same, but you're not proving that those n cases are the same, so you're saying that, as you said, the horses are both green and blue.
Yeah, which we can't have. Right, if this horse is green, it's green. It doesn't matter if I put it in a field with these other horses. So now I pick up these 5 horses and I put them in there, the fact that this one's green means that all of them have to be green.
I think one of the issues is when you're sitting there and saying P of 1 horses is the same color, so
Mhm.
with the set of 1.
Right.
Then you use that assumption that a set of 1 horse is the same color to create a assumption that all horses of, the set of N horses is the same color.
Mm-hmm.
Then you're using that set to prove that a set of N plus 1 horses are the same color. So
You're very
constantly
close to it.
increasing your set, but you're kind of specifically generating your set to prove your,
But logically, that's allowed. The problem is in what you just said, but logically, that's allowed. We prove P of 1, and then we assume P of n. We can always assume P of n. We're not proving P of n is true. All we're proving is this. It's a proposition. We're not actually proving that this is true yet. We're just saying if this is true, then this is true. But that combined with this, combined with mathematical induction, that's what gives us all P of n. But you said something that contains the problem.
P of 1 seems like a very different case than P of 2,
Why?
because one horse by itself is always going to be the same color, whereas 2 horses can have different colors.
Oh, what we're saying is P of n implies P of n plus 1. We can't say that it implies P of n plus 1. Is that the problem in this particular case?
Kind of combined with what you're saying.
Yeah, because having one horse is always going to have the same color as all horses.
And that's okay, that's legal. We'll find trivial base cases all the time when we do this. But here's the question. Does P of 1 imply P of 2?
Right.
And we know logically it shouldn't. What's wrong with our proof?
It's based on the idea that P of 1 implies P of 2.
It's not directly. What did we do in our proof that Pn implies Pn plus 1? We said, well, here's 2 horses. Any group of 1 horse has the same color. Everything in this group has the same color. Everything in this group has the same color. Therefore, they both have the same color.
Yeah.
But I snuck something in on you. If you assume P of 2, any group of 2 horses have the same color. These horses are the same color. These horses are the same color. This is the one that makes 1 and 3 the same color. But this doesn't work if you try to use P of 1 to imply P of 2. This proof only works if there's an overlap between the first n and the last n horses. So if I have 5 horses, if I have 6 horses, the first 5 and the last 5, they overlap on these. That's what forces all of them to have the same color. But if I have 2 horses, the first one and the last one, they don't overlap. And my inductive step does not work for that case. I picked a base case that was too small. You need to know that your inductive step applies for all values starting with your base case. And in this case, it doesn't. It only works from 2 on up. Now, if I could prove P of 2, then this is an airtight proof. And in fact, if any 2 horses have the same color, it's trivial to see that all horses have the same color. Because you can take 3 horses, break them into 2 pairs, and go from there. So that's a really sneaky error. And it's about choosing the base case.
But what if we say P of 1 is equal to P of n,
Mm-hmm.
and if we say 5 horses is the same, just the first step,
Mm-hmm.
and it's proven because it's we are assuming that, right? Then we are going to have another set after that.
Well, and we've proven that if all sets of 5 horses are the same color, then all sets of 6 horses are the same color. And that's in fact true.
Can I write something about?
Okay.
So, I'm saying like, here are 5 horses,
Mm-hmm.
blue, another 5 horses, these are red,
Okay.
And this doesn't have overlap,
Okay.
so this is fine, right?
Yeah.
then we're gonna have another one over here. This over here is P of 1. This over here is P of n. And we can attach all of these together. So this is going to be
P of middle,
Mm-hmm.
then this should be same color. And we have the overlap over here.
But how are you going to prove that inductive step?
We are assuming that.
And do you have a base case for which it's true?
It's same thing. This is P of 1.
But that's not true for any set of 5 horses.
We are saying it's true. We are assuming that it's true.
If it were true for any 5 horses, then you would have proven that all of these horses are the same color.
Yeah, that's what I'm going. So we can prove this.
But we can't prove P of 1 because if I take 2 horses from here and 3 horses from here, P of 1's not true for that set.
But if we go all the way to infinity,
Mm-hmm.
then we're gonna find and get all these middle sections, middle steps. We're gonna attach all of these together, and they're gonna be same color, while they are not same color. Because this set is red, this set is blue, and this set could be green, but this is
Right, but I
also-
don't think you can
also
prove your
blue
base
and-
case. I don't think you can prove P of 1 is true for all sets of 5.
You'd have to do another induction proof for P of 1.
for P of 1.
Because you can't assume P of 1 is true, you have to prove it. And then you're
Right.
assuming that P of n is true. The
Or you
assumption
have
part
to
is
know
only
something
for,
about horses that make it true.
yeah, the assumption part is only for n. P of
Right.
1 has to be really true.
Really true.
Yeah, it can't be assumed because then your base case is an assumption and your inductive case is starting on an assumption. So you've never actually proved that anything about it is true.
Can we just
That's a good way to
select the first step for that? Like 5 horses, 5 green horses?
No, it's gotta be true for all. You're assuming when you use it here, that it's true for any set of 5. So you can't just pick a particular 5 and say P of 1 is true. Because what you're actually using is the fact that it's true for any, right? So write out in full detail what P of n is stating, and then see if you can make P of 1 true, and I think you'll find you can't.
Okay.
And we're kind of waving our hands about what these propositions are. I wrote them yesterday. But try writing out exactly P of n is the proposition that, and spell it out, and
How
then
did you
see.
prove the P of 1 on the main question?
Because if you have one horse in a field, all the horses in the field are the same color. No matter what horse you put out there. So for any collections of one horse, all the horses in that collection are the same color.
Now, let's say if we specifically were to say, go out and get 5 horses of the same color and have only those horses in the field, does that prove P of 5?
No,
That's a case.
that's a case. Right?
Yeah, so
That's-
that,
P of 5 is the proposition that any set of 5 horses will have that property.
Alright, that one is there.
So,
then you have to get all the horses in the world and break them up into 5 with each individual horse every time, and then you'd be good.
just like we can say P of n is the proposition that n is equal to 2 times n. And we can prove absolutely that P of 0 is true, but we can't prove that P of n implies P of n plus 1. Which stops us from proving that this is true for all integers. So we can use induction for lots of things, okay? Sometimes incorrectly, and some of the incorrect uses are pretty subtle. Let's talk about pie fights. So the odd pie fight problem. So here's a setup. You have a group of people, they walk into a room, and as they walk in, you hand each one a pie. And they go and they stand somewhere in the room. And the only rule is you have to have unique distances between all people. You can't have 2 people who are exactly the same distance from each other. Okay, so got to have different distances.
2 pairs of people or 2 people?
Yeah.
2 people.
Okay. Wait, what?
So if you put 3 people in the room, you couldn't have them exactly a meter apart from each other.
That's two sets of people though.
So the two sets, because.
Two people will always be the same distance
Yeah.
from each other.
Because person
Right.
A is going to be
Okay,
the same
okay.
as person B.
Right, so the distance between any two people is unique
I mean, it's some weird like
over all the distances.
Euclidean.
No.
So I was like,
Does
that
it
doesn't
have to
seem
be,
possible.
like, what dimensions are we modeling here?
Infinite sized room.
Okay, but like, is it 2D or 1D?
Two-dimensional. So it's just a regular room, and you can stand on the floor, but you can't float.
Add another dimension. just
Yeah,
based
so a
on-
top view of the room. So some way of pick some point, like the center of your pie maybe, right? And you can measure your distance to everybody else in the room. And you can measure the distance of each person to every other person, okay? That set of distances, no repeats. The reason is, what you're going to do is you're going to throw the pie at the person who's closest to you. And we want that to be well defined. Okay, so that's not a trick, I'm not sneaking something in on you. So you walk into the room, each person is holding a pie, you go and stand wherever you want, and when the whistle blows, each person throws the pie at the person closest to them. And the question is, will everybody get hit by a pie? And if there's an even number of people, it's entirely possible. For example, you could have 4 people like this. And the person closest to A is B, so they throw their pie at B. The person closest to B is A, they throw their pie at A. And same thing over here. And all 4 people end up getting hit with a pie. The interesting thing is, if you have an odd number of people, there will always be at least one survivor who does not get hit.
You can't arrange it in such a way that the last person throws the pie at the first?
You could, but not if the distances are distinct. For example, if here's A and here's B, I can't put C exactly the same distance as this from A and B. So C might be down here. So A is going to throw at B, B is going to throw at A, and C is going to throw at whichever one they're closest to, A or B. So let's say they're a little closer to A, and C is the survivor. And it might not be clear how to prove this, but we can actually do it pretty simply with induction. So here's the setup. P of n in an in-person pie fight, there's at least one survivor. And since we're dealing with only odd values of n, I don't want to get into a lot of 2k plus 1, so I'm going to use a slightly different form of induction. I'm going to say prove p of 3, and then I'm going to prove p of n implies p of n plus 2, where n is odd, and then I'm going to conclude p of n for all odd n. And I can turn that into regular induction. P of k implies p of k plus 1 by doing some 2n plus 1 to get odd numbers. But this works. Okay, and it should make sense. If I can prove p of 3, I can use this to prove p of 5. I can use it again to prove p of 7 and p of 9 and so on. So I'm going to use this form of induction. I'm going to prove p of 3 and then prove p of n implies p of n plus 2. So p of 3 is pretty straightforward. It's basically what's on the board. If I have 3 people in the room, 2 of them are going to be closest to each other. Right? The total distances that I have are the distance from A to B, A to C, and B to C. And one of those distances will be the smallest. And whichever 2 people are that distance, they're going to throw their pies at each other. And then C has a pie, can't throw it at yourself, they're going to throw it at one of those 2 people, and nobody throws a pie at C. So you can argue by cases that P of 3 is true. So now suppose Now suppose we have n plus 2 people in the room. We're assuming P of n, where n's an odd number. So we're assuming that in a group of n people, there's a survivor in a pie fight. So now we bring 2 more people into the room. Okay, look at all n plus 2 people in the room, find the 2 people who are closest to each other. And let's call them A and B. Or let me just call them 1 and 2. And then we've got some other people. And that's not where they're standing in the room. But I'm calling 1 and 2 the people who are closest to each other. So I know without doubt, 1 is going to throw their pie at 2, 2 is going to throw their pie at 1. And I'm left with n people with n pies. And there's 2 cases. Case 1, somebody from here throws their pie at either 1 or 2. Might not happen, but it might. If at least one person throws their pie at one of these people, we're left with n people and only n minus 1 pies in this group. Nobody here has been hit by a pie yet. When n people throw n minus 1 pies, there's going to be a survivor. Because each person can get hit by 1 pie, and if you've only got n minus 1, only n minus 1 people can get hit. So if anyone from this remaining group of n throws a pie at either of these 2 people, we've got a survivor. The other possibility is that this doesn't happen, and we have n people and n pies. But by P of n, if we have n people with n pies, there's a survivor. And so we know there's a survivor in this group, and so there's a survivor in the entire room of n plus 2 people. So P of n plus 2 is true, and so P of n is true for all odd n.
Could you also show this by just saying that 1 through n leaves you with 1 survivor, and then you got P of 3?
Not necessarily.
No?
Because 1 through n, you could have somebody here throw a pie at you, or you could have somebody here throw a pie here.
Okay.
Right, when we put these people in the room, we don't know automatically that we can break it into a group of n and a group of 2. But we can argue that these 2 throw at each other, but we still have to deal with the possibility that someone here throws a pie into that group of 2. But yeah, pretty much the same thing.
Yeah. I guess I was thinking of it in the way that we were doing some of the other proofs where we kind of drop down the initial, because we know P of n leaves 1 survivor.
Mm-hmm.
And then you'd have the 1 survivor and then n plus 1 and n plus 2. So then you have P of 3, which you did already know is true.
Right,
Yeah.
right.
So in this certain type of problem, that's not necessarily an okay way to do it, but it's the same
Right.
principle.
Yeah, same principle.
Okay.
Yep. So we don't just have to prove things about factorials and series of reciprocals. Oh, and by the way, just to mention, that does not converge. So some people use that on their homework as an example of an infinite series that's not infinite. That actually is infinite. I didn't take off for it because he had the right idea.
Yeah, you have to have an exponent greater than 1, right?
Yeah. Maybe greater than, is it greater than 1 or greater than 2?
I think 2 converges.
2 definitely converges. I don't know if 1.5 does. But straight sum of reciprocals, that blows up. Which I burned like 6 weeks of time on an old TI programmable calculator in high school trying to show. It never got to infinity. But in case you bump into that in calculus. What?
Were you just hoping you would like show?
I was hoping it would get into like big exponential powers at least. And it didn't get very big. Yeah, it takes a long time.
What's the limit of this set be 0?
The limit of it is 0.
It does approach 0. That value does approach 0, but the sum
the sum blows up to infinity. It just gets bigger and bigger, even though the terms get smaller and smaller. It gets bigger quicker than the terms get smaller somehow. All right, I was going to do Towers of Hanoi, but I don't have time to do it right yet, so because I want to tie it into programming. So let's talk about postage. You're living in a country, and they only have 2 denominations of stamps. They have 4-cent stamps, and they have 5-cent stamps. And it always costs you at least 15 cents to send a letter. And the question is, for any denomination, for any postage 15 cents or greater, can you find a combination of those 2 stamps that adds up to exactly what the postage is? Sure?
Apparently.
Okay.
It reminds me of egg timer problems.
Okay.
So,
It's not true for all denominations, right? If I picked 5 cents and 3 cents, well, I shouldn't try to do this without a safety net.
What do you mean a safety net?
Without having done this before at home. But there are denominations you can come up with for which this doesn't work, right? And for example, a 4 and a 5, I don't think you can get 11 cents.
well, you said at least
Wait.
15 cents.
Yeah, because there's some denominations you can't get.
Mhm.
And I think for random
But it's
denominations,
just greater than 15 cents.
what?
It's just greater than
Yeah, if it's greater than or equal to 15.
11.
But can you prove that you can always do this? I'll give you a hint. You can do it with induction. Big hint.
And that went so well the last time.
Yes.
I think we're on the track.
How would that work? We're dealing with like 2 sets, aren't we?
Sort of. Can someone name a proposition that we can work with at least?
So let's say that if you have a piece of postage or a letter that you're sending to your grandmother costs N cents to mail, then you can mail it for 4 and 5 cents.
Okay. Let P of N be the proposition.
Or N is greater than 15.
Right.
So it's less than 15.
N equals something times 4 plus something else times 5. And N bigger than or equal to 15. So A is the number of 4-cent stamps, B is the number of 5-cent stamps.
So we would start at 15.
So for our base case, we're going to do P15. And can we get 15 cents out of those stamps?
Yeah.
Right? All we have to do is note that 15 equals 5 plus 5 plus 5. So P15 is true. So to induct, we want to prove P of N implies P of N plus 1. So assume P of N. So you've got the combination of 4s and 5s that give you 1 penny less than what you're after. Can we get this slightly more expensive postage? And you got to do this in cases.
Well, by cases
Well-
it's getting easier because we can do the thing that we learned about the remainder
Mm-hmm.
for 10. We had I think 6 of those,
Okay.
and we can split it to those cases and do for each other.
Okay, that might get us there. You got another
If
idea?
we have a case with a 4, we can just prove P of N plus 1 by replacing one of the 4s with 5, and that deals with, the only other case we have to deal with is without 4s, which would be all 5s.
Okay, so case 1.
You just prove induction for different groups and then go like P of N plus 5, and then we could prove for every 5 or something? Because right there with the 5 plus 5, we've proven that we can come up with any multiple 5 times.
We can come up with any multiple of 5.
Right.
for an arbitrary number n, if our solution to P of n involves at least one 4-cent stamp, we can just change it with a 5-cent stamp. Right? So in this case, n equals, a times 4 plus b times 5, and a is bigger than or equal to 1. We use one fewer 4-cent stamps and one more 5-cent stamp. And that'll bump us up by a penny. But case 2, we don't have any 4-cent stamps.
So it's all 5-cent stamps.
It's all 5-cent
And
stamps.
because it's carries 15, you can assume that there's at least 3 or more 5-cent stamps. So you could substitute 3 5-cent stamps for 4 4-cent stamps to get.
There we go. Replace 3 of your 5-cent stamps with 4 4-cent stamps. You'll take away 15 cents here, you'll add 16 cents here, that'll bump your total value up by a penny. So n equals b times 5, b is greater than or equal to 3, n plus 1 equals 4 times 4 plus b minus 3 times 5. And those are our only two possible cases. Either we have at least a 4-cent stamp or we don't. And in either case, we can make a simple substitution to increase our postage by 1. Therefore, P of n plus 1 is true. And then by mathematical induction, P of n is true for all n bigger than or equal to 15.
So given 2 values of postage, how would we figure out what the at least value is?
Oh, I did it by trial and error. There's probably a good way to do it, though. That's an interesting question.
What's interesting?
I guess you have to figure out ways to increase by, say, a penny if that's your target, and you're trying to find a linear combination of these. Maybe that comes out to 1 or minus 1.
Yeah, I wonder if you could do that without 2 values of stamp that are right next to each other. Because you're relying on taking away, moving around with 1 penny, right?
Yeah.
So what if you do like 7 and 10 or something like that?
Yeah, so if you do like 3 and 5, right,
You
if
can't
you've
do
got
one
a
penny.
bunch of 3s, you can replace them with 2 5s and go up by 1 like that.
Yeah.
If you don't have any 3s and all you've got is 5s, I'm not sure you can get up by 1.
Yeah.
But there may be other pairs for which this works. And currency denomination is the standard example of this. We have 1, 5, 10, 25, and you can get all your denominations out of
This
those.
is a really
But the penny helps. Say what? Yeah, it's an interesting country. It's 4 or 5 land. So I want you to keep this in mind because we can use this to actually write a program that, given a number n, tells you what combination of 4-cent and 5-cent stamps to use. And we'll do that on Monday. And it'll be another version of when we tiled those square regions with L-shaped tiles. The proof that we could do it actually gave us an algorithm for doing it, a slow algorithm, but it let us break the big problem down into smaller problems. And this, if we have a solution for P of n, we know how to get a solution for n plus 1. We've got 2 cases. And if we don't know how to solve it for n, we can solve it for n minus 1 and then turn the solution into a solution for n. And if we don't know how to solve it for n minus 1, we can solve it for n minus 2. And we can keep working until we get down to 15, and we have a hardwired solution for 15. So we can actually use this proof that this is possible to actually come up with an algorithm to find the solution for any number n, bigger than or equal to 15. So we'll play around with that on Monday, and then we'll look at Towers of Hanoi, which is another example of something we'll prove inductively, but it will actually give us a solution for how to solve this game. And that'll sort of take us on our exit path out of mathematical induction and into the next topic, which will be counting. We'll spend a week talking about counting.
It's very hard.
Because it's really hard. There's a whole chapter in the book on it.
Oh.